ENIAC human computers. The year is 1942. The world is engulfed in the flames of the Second World War, a conflict being fought not just on battlefields, but in laboratories and on chalkboards. In the United States, at the Aberdeen Proving Ground in Maryland, a critical bottleneck is threatening the effectiveness of the Allied forces. Every new artillery gun, every new shell required a firing table, a complex chart that told soldiers how to aim their weapon to hit a target miles away, accounting for everything from wind speed and air density to the curvature of the Earth. Each table required solving hundreds of complex differential equations, a mind-numbing task that could take a single, highly skilled person over a month to complete. With the war machine demanding new weapons constantly, the Army was drowning in a sea of uncalculated numbers. The solution, at first, was human. The Army recruited hundreds of women, many with degrees in mathematics, who were previously denied opportunities in their field. They were given a title that sounds strange to us today. They were called computers. A vast room filled with women, each armed with a desk calculator, a slide rule, and a sharp mind, worked in a relentless, coordinated effort. They were a human processing unit, breaking down monstrous equations into smaller, manageable steps, passing their results from one to the next in a kind of analog assembly line of pure mathematics. This was the Moore School of Electrical Engineering at the University of Pennsylvania, the epicenter of the Army's computational efforts. The work was grueling, the pressure immense. A single error in a single calculation could render an entire firing table useless, potentially costing lives on the battlefield. These women were the unsung intellectual force behind the war effort, their contributions as vital as any factory worker or soldier. But even their combined brilliance couldn't keep up with the relentless pace of the war. The military needed something faster, something that could calculate in minutes what took a human computer weeks. They needed a machine. Enter John Mauchly and Jay Mauchly, Presper Eckert, two brilliant engineers at the Moore School. They proposed a radical, almost science fiction solution, an electronic computer, a machine that could perform calculations at speeds 1,000 times faster than any human. The project was codenamed Project PX, and the result would be a machine that would change the world, the Electronic Numerical Integrator and Computer, or ENIAC. The scale of the project was staggering. The ENIAC was a behemoth, a true titan of technology that, when completed, would occupy an 1,800-square-foot room. It weighed over 30 tons and was comprised of 40 separate 9-foot-tall panels. Inside its metallic shell was a dizzying maze of over 17,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, and 6,000 manual switches. Its construction was a monumental feat of engineering, a testament to wartime innovation. But as this colossal brain of wires and tubes took shape, a fundamental problem emerged. The ENIAC was a powerful calculator, but it was also, for all intents and purposes, brain dead. It was a piece of hardware, a collection of potential. It knew how to add, subtract, and multiply at lightning speed, but it didn't know what to calculate or in what order. It needed instructions. It needed to be programmed. Today, we understand programming as writing code in a language like Python or Java. But in the 1940s, there was no code. There were no programming languages, no operating systems, no instruction manuals, no precedent for this kind of work whatsoever. The very concept of software was a ghost, an idea that hadn't yet been born. The task of programming the ENIAC was seen by the male engineers as a secondary, almost clerical task. They had built the great machine. Figuring out how to operate it was someone else's problem. So they turned to the people who understood the complex ballistic equations better than anyone, the human computers. In 1945, the Army placed a notice seeking out the most brilliant of the Moore School's female computers for a top-secret new role. They weren't looking for engineers or physicists. They were looking for mathematicians with a deep, intuitive understanding of logical flow and complex calculation. From a pool of hundreds, 6 women were chosen. They were told they would be the first operators of the ENIAC. But operator was a gross understatement. They weren't going to be pushing buttons. They were going to be giving the machine its mind. They were about to step into a completely unknown world and invent the very discipline of computer programming from first principles, using nothing but their own intellect, giant blueprints of the machine's wiring, and a problem that had stumped the entire U.S. Army. Their names were Kathleen Antonelli, Jean Bartik, Betty Holberton, Marlyn Meltzer, Frances Spence, and Ruth Teitelbaum. And the world was about to be remade by their invisible labor.
Pioneering female programmers. When the 6 women were finally granted security clearance to see the machine they were supposed to program, they were stunned. Before them stood the ENIAC, a black, metallic labyrinth of switches and cables, utterly silent and imposing. And they were given almost nothing to work with. No one taught them how to program it because no one knew how. The male engineers who built it, Eckert and Maudsley, were brilliant hardware architects, but they had little interest in the nitty-gritty of making it run problems. The women were handed a stack of enormous, complex block diagrams, the machine's blueprints, and the differential equations they needed to solve. That was it. Their task was to figure out how to make the machine execute the mathematical steps they themselves used to perform by hand. This wasn't just a new job. It was the creation of a new form of human thought. Programming the ENIAC was a brutally physical and intensely mental process. To input a program, the women had to first break down a complex equation into the smallest possible logical steps that the machine could handle. They would spend weeks huddled over paper, creating detailed flow diagrams, the very first of their kind, mapping out the entire sequence of operations. Then came the physical implementation. They had to manually wire the program into the machine itself. This meant walking up to the massive panels and physically plugging and unplugging hundreds of cables into a series of giant plug boards, similar to old-fashioned telephone switchboards. Each cable represented a piece of logic, a connection that told the machine where to send a number after an operation was complete. They also had to set thousands of switches on the machine's function tables to input numerical constants. A single program could take days or even weeks of meticulous backbreaking work to wire into the machine. One wrong plug, one misplaced switch out of thousands, and the entire calculation would fail. This process led them to invent one of the most fundamental concepts in all of computer science, debugging. The ENIAC was notoriously unreliable. Of its nearly 18,000 vacuum tubes, several would burn out every single day. When a calculation produced an error, the women had to figure out if the problem was in their logical programming, a bug in their thinking, or if it was a hardware failure. This often meant a painstaking hands-on search. They would crawl inside the massive machine, manually checking each of the thousands of soldered joints and vacuum tubes, often with a pocket mirror, to find the source of the failure. Jean Bartik recalled how they would run a problem on 2 identical units of the machine simultaneously. If the results differed, they knew a hardware failure had occurred, and the hunt for the faulty tube would begin. They became so intimately familiar with the ENIAC's architecture that they could often diagnose problems faster than the engineers who had built it. But their genius went far beyond just wiring and debugging. They were true architects of software. Facing the daunting task of programming the machine for its first major, top-secret problem, a complex simulation for the Los Alamos laboratory related to the hydrogen bomb, they realized that writing one monolithic program was impossibly inefficient. It was Betty Holberton who had a breakthrough idea. She proposed creating small, reusable sets of instructions for common mathematical operations, which they could then call upon whenever needed. She invented the concept of the subroutine. This was a monumental leap forward. Instead of rewiring the same logic over and over, they could create a master program that would intelligently switch between these smaller pre-wired routines. This innovation not only saved them immense amounts of time, but also laid the foundational groundwork for all modern software development. Every programmer today who uses a function, a library, or an API owes a conceptual debt to Betty Holberton and her team. They were designing the very structure of software, inventing the rules as they went. They were not just operators, they were the ENIAC's true masterminds, transforming a powerful but dumb machine into a versatile problem-solving marvel. They were, in every sense of the word, the world's first software engineers. Erased legacy women in tech. In February 1946, the ENIAC was finally revealed to the world. The Army organized a lavish press event showcasing their new electronic marvel to journalists and dignitaries. They demonstrated its incredible speed, calculating a ballistic trajectory in just 20 seconds, a task that would have taken a human computer 40 hours. The press was ecstatic, hailing the machine as a giant brain and celebrating the two lead engineers, John Mauchly and J. Presper Eckert, as its visionary fathers. The event was a triumph. But as the cameras flashed and the men took their bows, the 6 women who had given the giant brain its mind were completely ignored. They were not introduced. Their names were not mentioned in the official press releases. They were, in the eyes of history, invisible. That evening, a celebratory dinner was held for the individuals who had made the project a success. Not a single one of the 6 programmers was invited. In the days and years that followed, this erasure became systematic. When photos were taken for publicity, the women were often told to stand beside the machine and point at its panels, as if they were merely showcasing the hardware. This led to a deeply insulting narrative that they were simply models, sometimes dismissively called refrigerator ladies, posing with the latest home appliance. The complex intellectual work, the weeks of designing logical diagrams, the invention of subroutines, the painstaking process of debugging was completely written out of the story. The official history solidified into a simple, male-centric narrative. Mauchly and Eckert built the hardware, and the hardware was the only thing that mattered. The act of programming, the software side of the equation, was deemed unimportant, a soft secretarial skill. It was seen as women's work, and therefore it was not seen as innovation. This historical malpractice had profound and lasting consequences. By erasing the ENIAC programmers from the origin story of computing, it created and perpetuated the myth that computer science was a field pioneered exclusively by men. As computing evolved from a scientific curiosity into a global industry, this foundational myth became embedded in its culture. The image of the programmer became that of a man, often a hobbyist, who grew up tinkering with electronics in his garage. This narrative created a cultural barrier, subtly and overtly discouraging generations of women from entering a field their predecessors had invented. The pioneering work of Kathleen Antonelli, Jean Bartik, Betty Holberton, and their colleagues was not just forgotten. Its absence created a void that was filled with a false history, a history that has contributed to the gender imbalances we still see in the tech industry today. For nearly 50 years, their story was lost. It wasn't until the 1980s that a young computer science student named Kathy Kleiman stumbled upon a photograph of the ENIAC. She saw the women in the picture and, like everyone else, assumed they were models. But her curiosity was piqued. She began to dig, embarking on a decades-long quest to uncover the truth. She tracked down the surviving programmers, recorded their oral histories, and painstakingly pieced together their forgotten contributions. Her work became the ENIAC Programmers Project, a determined effort to write these 6 women back into the history they had been so unjustly removed from. Thanks to Kleiman's tireless advocacy, the story began to change. In 1997, the 6 original programmers were inducted into the Women in Technology International Hall of Fame. Posthumous awards and recognitions followed. Their story is a powerful, infuriating, and ultimately inspiring reminder that history is not always a fixed account of what happened, but a narrative that is written and sometimes must be rewritten. The mothers of programming were not models. They were architects of the digital age.